Dear students, welcome to a new video for Pure Mathematics course. Now we will start a new topic for the matrices. Here is the matrix definition, which is a matrix consists of m horizontal rows and n vertical columns. It's called m by n matrix or matrix with size m by n. Now you should know that the size of the matrix is very important to be determined to our solution. We first say the number of rows, then we identify the number of columns. So a matrix is a rectangular array of numbers and consists of n horizontal rows and then n vertical columns. Now this size of the matrix here will be m I mean m rows and n columns. For every entry in the matrix, we call the aij. I is the row subscript and j is the column subscript. Here is 1, a11, it means it's the first number or symbol in the matrix where the first row and first column. Here a12, this means that the first row and the second column. And here up to a1n, I mean this in the first row and the nth column. As the same for the columns, here is the am1, this means that we have m number of rows and n1 is the first column. Here amn is the number of rows equal to m and the second column up to amn. So the size of the matrix is determined by first the number of rows, then the number of columns. Let's exercise or have examples for the size of the matrix. This is first a matrix. This is a vector where matrix 1, 2, 0. This means the size of this matrix is 1 by 3, not 1 multiplied by 3. 1 means 1 is the number of rows and 3 are the number of columns. So 1 by 3 is the size of the matrix. Number P, the matrix here consists of number of rows, 3 rows, and the number of columns equal to 2 columns. So the size of the matrix is 3 by 2. Another example here is only one number, or maybe it's a sample, but it's only one. Once it's in the brackets of the matrix, we consider it a matrix. So the size of this matrix is 1 by 1. Here, the last example of this matrix, let's count 1, 2, 3. This means 3 rows and 1, 2, 3, 4, and 5. This is 5 columns. So the size of the matrix is 3 by 5. Now we are qualified enough to know the size of each matrix. Now, the equality of the two matrices, where A it consists of A, Ji, and P matrix it consists of P, Ji are equal if they have the same size. If they have the same size, so we can say two matrices are equal even it's not have the same size. So we can transpose the matrix A if we have this matrix A with size how this the matrix of this size is 2 rows and 3 columns. So this matrix is 2 by 3. This is the size of the matrix. Now, if we want to get A transpose, A to the power T, this means the transpose of the matrix. Simply transposing the matrix means that we will transfer the columns to P rows and the rows to P columns. You just transfer them and all the numbers and all the signs are the same. So A transpose will be 1, 2, 3 at the columns. The first row will be the first column and the second row will be the second column. So the new transpose matrix will be 1, 2, 3 and the second column 2, 4, 5, 6. If we get A transpose all R transpose, this means that we get again the first matrix, which is A. So A transpose all is transpose equal to the same matrix or the basic matrix, which is A. Another very important definition, which is the matrix addition and scalar multiplication. Now, the rule for add two matrices is the two matrices should be at the same size. We can also add or subtract any two matrices except they have the same size. Now, let's move to the example number routine where the matrix addition. The first one The first matrix consists of 3 rows and 2 columns. The size is 3 by 2. And the second matrix is 3 rows and 2 columns. The size is 3 by 2. Now we get the rule for the addition and subtraction, which is that the two matrices have the same size, so we can add the two matrices, and it's no problem for adding this. Now we will add by adding each number to the corresponding number to it in the other matrix. So we'll add 1 plus 7 to equal to 8, and 2 in the first matrix with minus 2 in the second matrix to be 0, and we will move to the other row or the second row, which is 3 added to negative 6 to be negative 3, and 4 added to 4, which is equal to 8, and finally the third row, which is equal to 5 added to 3 in the second matrix will be 8, and finally 6 to the corresponding number in the other matrix, it's equal to 0, so it will equal to 0. Now we will have the result code in the same size also, which is 3 by 2, because we add two matrices with the same size. The same calculations will be if we have a subtraction sign. If we have the subtract the two matrices, now we will do the same steps by subtracting the first number from the other number corresponding to it in the next matrix. Now we will move to the other example, number P, where we have add the first matrix 1, 2, 3, 4, adding to the vector 1 and 2. Let's first get the size of the first matrix, which is 2 by 2, and the second matrix is 2 by 1. Now, the rule for size is not applicable, and the first matrix must have the same size for the second matrix, so it's impossible that as the two matrices are added because they haven't the same size. Scalar multiplication. Scalar multiplication means that we will multiply a number or a constant or a symbol by a matrix. This matrix may be the result for addition to matrices or only one matrix, or maybe it's a zero matrix. All the results will be multiplying only one number to each number in the matrix. This is what's meant by scalar multiplication. Let's take an example. If you have two matrices like this size 3 by 2, and the second matrix is 3 by 2, we can simply subtract two matrices from each other by subtracting each number to the corresponding from the second matrix equal to 2 minus 6, 6 minus 2. Please take care from the negative sign for the number and also the sign for the subtraction, which is minus. So 6 minus 2 equals 6 plus 2 to be a positive 8, and also negative 4 minus 4 equal to minus 8, and 1 minus 1 equal to 0, and for the same for all the number in the two matrices. Of course, the result of the subtraction will be also 3 by 2 because we have the same sizes subtracted from each other. Now We will take another example. It may be more advanced, a little more, which is if we have two matrices A equal to 6, 0, 2, -1, which have the size 3, 2 by 2, and another matrix P equal to 3, -3, 1, 2, which is the size is 2 by 2 also. Get how to calculate A transpose minus 2P. It's very important calculations because it's more advanced, a little more, and this is we will first should get A transpose, then get the scalar matrix 2P and subtract the two results from each other. If we get the first A transpose, this means that we will get the rows columns and the columns rows like this. 6, 0, 2, -1 will be the first column 6, 0 and second column -2, -1. This is the A transpose. And to get 2P, this is a scalar multiplication, which we will multiply 2 by each number in the matrix P. So 2 times P times 3 equal to 6, 2 times -3 equal to -6, 2 times 1 equal to 2, and finally 2 by 2 equal to 4. Now we have A transpose and 2P. We will subtract the two matrices from each other by subtracting each number by the corresponding number in the second matrix to get the final matrix, which is 6 minus 6 equals 0, and 8, the second row is -2 and -5. This is the final result for A transpose minus 2. Now, let's know that we have a scalar, to get the scalar multiplication definition and examples. The zero matrix is a matrix is consists of all values are zeros, and matrix and identity matrix is the matrix, very important to look at matrix. Identity matrix is a square matrix. Take care, in this identity matrix is a square matrix. A square matrix means that the number of rows equal to the number of columns. It may be 2 by 2, 4 by 4, 3 by 3, 5 by 5, any numbers that the number of rows equal to number of columns. This means a square matrix. So again, the square matrix is a matrix that the number of rows equal to number of columns. Now, what's the identity matrix? Identity matrix is a square matrix where the diagonal is equal to 1 and all other values is equal to 0. This means we have only the diagonal is equal to 1 and the upper triangle and the lower triangle equal to 0. Note that the diagonal should get from left to right, not from right to left, and equal only 1, not -1, not 0, only 1. And all other values in the diagonals, except the diagonals, is equal to 0. So we have two triangles are equal to zeros, like this. Here, 0, not 6, 0, 0, 0, 3 zeros, and here 3 zeros, and the triangle is equal to, and the diagonal equal to 1. That's just that for a square matrix. Of course, it's by logic because the matrix which is not a square, it not have a diagonal. So should be the diagonal matrix, and all the diagonal is equal to 1, and all other values is equal to zeros. And the diagonal with +1 from left to right. Okay, so this is the identity matrix. Now let's move to a very important topic, which is the matrix inverse. Matrix inverse. The matrix inverse, which is denoted by A to the power -1. This does not mean that the matrix is to the power -1. No, it means that we have the inverse of the matrix. Take care that the inverse of the matrix is completely different for the matrix transpose. In matrix transpose, we just move the columns to be rows and rows to be columns. But now, in the matrix inverse, we get all the values for the inverse, or the other hand of the matrix. Now, to get the matrix inverse, we should first get the matrix determinant. The matrix determinant, which is a value for the matrix. The matrix determinant means we have only one value for the matrix, and calculated for the square matrix with size 2 by 2 as follows. Take care that we have this the rule for determinant matrix determinants for the only matrix with size 2 by 2, and we can get the determinant for any matrix that is a square matrix. At the beginning, we will begin by the matrix size 2 by 2. So this matrix, if we have matrix with A, P, C, D, 2 by 2, we have 2 rows and 2 columns, we can get the matrix determinant, which is denoted by A in between 2 lines here. This means the matrix determinant equal to, take care here, A times P, here from the left to the right, A times D, A times D, multiply negative sign minus, okay, minus P times C. Again, to get the matrix determinants for a matrix with size 2 by 2, for a square matrix 2 by 2, we apply this rule. A times D, if we have the matrix A, P, C, D, A pi times D here, minus P times C here, to get this row. So this is the A determinant. Here we will get a value, a number for the matrix. For example, if we have the matrix A and 1, 2, 3, 4, the A determinant and the value for this matrix will be 1 times 4, okay, minus 2 times 3, to get 1 times 4 equal to 4 and 2 times 3 equal to 6. So the matrix determinant in this case is equal to negative 2. Take care, this is a negative sign here, so it will be a negative 2. Now here, this is the value for A determinant. We said a value for the matrix with size 2 by 2. But we want to get the value for A inverse. A inverse, or the inverse for the matrix A, is equal to this rule. Applying this rule, A inverse equal to 1 over A determinant that we get from the previous rule times this matrix. What is this matrix? Note that we change the A and D but location, but not change the signs. Okay, and in the other diagonal P and C, we set the location as it and only change the sign for P and C. Again, here in to get the inverse matrix, applying this rule, A inverse equal to 1 over A determinant multiplied by the matrix. We will change the, here we will change the location for this diagonal and not change the sign. So A and D, we will get D here in the first number and A in the last number in the matrix. And for the other diagonal here, we will set the location the same and it changes the signs only. Okay, let's move again to the example to apply this rule. Here, A inverse will be equal to 1 over A determinant, which we get from the first step, which is equal to negative 2. So 1 over A determinant will equal to 1 over negative 2. And applying this rule, we will get A and D, change the location of this diagonal without changing the sign. 1, 4, 1 and 4 will be 4 and 1 here, like this. And the other diagonal, we will set the same location for 2 and 3 and just change the sign. So it will be -2 and 3. Now we will ready to get a scalar multiplication by multiplying 1 over -2 to every number in the square matrix for this value. So we'll multiplying 1 over -2 times 4 equal to 4 over -2, 1 over times -2 times -2 and times -3 and times 1. So the A inverse will be this form. Take care, it's a very important topic in our matrices exam. Finally, we will move to the matrix multiplication. As we said that the size is a very important rule in the addition and subtraction, and to the two matrices or three matrices should have the same size to be added or subtracted from each other. Now for a multiplication we have very important rule, very important rule. Note that now to multiply two matrices from each other, the number of columns in the first matrix should equal to the number of rows in the second matrix. Again, to be multiplied or to multiply two matrices, you should apply the rule that the side of the matrix is consistent. So, to multiply two matrices, the number of columns in the first matrix should equal to the number of rows in the second matrix. For example, this matrix have 2 by 3 because it have 2 rows and 3 columns, and this matrix is 3 by 3. This matrix, two matrices can't be added because the number of rows and columns are different in the two matrices, or the size at all is different from matrix A and matrix B. But these two matrices can be multiplied. Let's apply the rule. The rule of multiplication is the number of columns in the first matrix should equal to the number of rows in the second matrix. So we have really this number of columns in the first matrix is 3 columns, and the number of rows in the second matrix is 3 rows. So we can multiply the two matrices. And the size of the matrix will be 2 by 3. Now, let's take a more practice exercises and examples for the matrix product. Answer A, compute the vector 1, 2, 3 by 2, 5, 6. Now, let's first get the size of the two matrices we have. The size of the first matrix is 1 by 3, and the size of the second matrix is 3 by 1. So, we have the number of columns in the first row equal to the number of rows in the second row, and we can multiply the two matrices, and the value will be a matrix with 1 by 1. Let's now know how to multiply two matrices by each other. First, we will add the first with multiply the first with the first, then adding 2 by 5 and then 3 by 6. Again, 1 by 4 equal to 4 plus 2 times 5 equal to 10, 14 plus 3 by 6 equal to 18, and the total summation is equal to 32. Let's move to another example for the matrix multiplication. Here, 1, 2, 3 is a matrix with size 3 by 1, and this matrix is 1 by 2. So the two matrices can be multiplied by each other because the number of columns in the first matrix is equal to the number of rows in the second matrix. And the final result with a matrix with a size 3 by 2. Let's now begin to multiplying process. Here we will multiply the first row with the first column. 1 times 1, 1, plus 1 times 6 equal to 6. So 1 equal 1 plus 6. Okay, and the second, then the first row with the first column, and the second, then 2 times, okay, 1 times 1 plus 1 times 2 plus 1 times 3, okay, equal to 6. And so on until we have the 2 rows and 3 rows and the 2 columns. Now let's move to another topic or another size of the matrix, which is 3 by 3 times 3 by 3. Of course, we can add or subtract the two matrices because they have the same size, and also we can multiply because the number of columns in the first matrix is equal to the number of rows in the second matrix, and the result will be 3 by 3. Now we will how to multiplying the two matrices. Let's note, we will first take the first row with the first column. 1 by 1 equal to 1 times 3 times 5 equal to 15. 15 plus 0 equal to 0. Then 1 plus 15 equal to 16. First row with the first column. We finished. Okay, let's move to the other column. We're still in the first row. We're still in the first row. We don't move to the second row until we finish all the columns. Now we will get the first row with the second column. The first row with the second column. 1 times 0, 0, plus 1 times negative 1, negative 3, plus 0 equal to negative 3. And get the value here because we do this for the first row. So the answer is in the first row. Now we finish the second column. We will move to the third column. Here, we now still finishing all the columns with the first row. 1 times 2 equal to 2, plus 3 times 3 equal to 9, 9 plus 2 equal to 11, and here the answer. We finished this third column. Is there any other columns left? No. So we will move to the second row to be multiplied by the 3 columns as we did in the first step. Here, the second row with the first column. Negative 2 times 1 plus 2 times 5 plus 1 times 2 equal to 10. And here we finished with the first column. Okay, we will move to the second column. So the second column with the second row, negative 2 times 0 plus 2 times negative 1 plus 1 plus 1 equal to negative 1. And finally, the third column with another example for the matrix operations involving identity matrix and zero matrix. Here, if we have a matrix A, which is the size is 2 by 2, and matrix P also 2 by 2 matrix, and matrix identity matrix with a square matrix, and the diagonal is 1 and all other values are zeros. And finally, zero matrix is a square matrix and all the values are zeros. First, we want to compute the identity matrix minus the matrix A. So we will get in the order. First, the identity matrix minus the A matrix is equal to these values. We subtract the value from each corresponding one in the other matrix. Then move to the P primes, which we want to compute 3 times A minus 2I. Please note that you should get the values for each one first, then the other value or the result value multiplied by 3, which is the scalar multiplication. So we first get 2 times the identity matrix value, which is equal to 2 times 1, 0, 0, 1. So will equal to 2, 0, 0, 2. And then subtract from 8, which is A minus this value. And the final result of this matrix is all multiplied by 3, which is multiplication or scalar multiplication. Now we will move to number C, which is A times 0 matrix. Of course, if we multiplying A matrix A with 0 matrix, the result without any calculations will be all are zeros. And here the matrix A times B will equal to the value of matrix A and B. Since we have the size is 2 by 2 and the second matrix is 2 by 2, they can be multiplied by each other and the results will be the identity matrix. Note that the matrix P is the inverse for matrix A, so the multiplication result is I. Here is all the topics for the matrix and the associated rules for multiplication and addition and subtractions. Practice more in the matrices. It's very important and simple topic, and see you again. Thank you.